All right, thank you, and I would like to thank the organizers for inviting me and for setting up such a nice conference. I should also thank these three things. The first one gives me an office, the second one pays my salary, the third one gives me some money to travel. So it's good. All right, let's start. So this is more or less the outline. I will first introduce this principle. The capitalization, it's a bit weird. I think it was introduced by Elias Farah, and he chose this capitalization. I never understood why. He doesn't know, but now it's like that. So the W, it's not capitalized. I don't know. Then I will introduce the coarse version of it, which is something I came up with. And then if time allows it, I want to sketch a bit how can you prove these statements here. All right. So let's start from the the topological case. So I want to understand how Čech Stone remainders of nice reasonable spaces behave and how maps between them behave. So Čech Stone, I used to say Stone Czech, but then Dana Bartoshova, she said it's Čech Stone, and you don't contradict a Czech person on the Czech word. So now it's Čech Stone. All right, and then I'll move to the coarse version. And whenever I say compact, I mean Hausdorff, right? In France, it is like that. So actually, it's very good that we had Maria's talk yesterday, because now we know, well, we should know anyway, but we have seen the Čech Stone compactification in the remainder. Just as a reminder, beta of X is the smallest compact space in which X sits densely. You can make this formal. It's constructed via universal property. So it's a compact space in which X embeds densely, such that any continuous map to a compact space extends uniquely. Okay, from F you get beta of F, and the restriction of beta of F. Well, I guess the point is like, yeah, that's right, but you don't have these. I mean, any bigger one X will not sit densely. Let me say it this way. Yeah, right. I mean, for the universality. And the remainder is whatever is left, right? So you pick X inside beta of X, and then you have X star, which is whatever I didn't consider, and this from X. And the points here are really non-principal ultrafilters on the space of closed zero subsets of X. Okay, and but I will approach this dually. So I'm using sister algebras. Whenever I say CBX, I really mean complex valued, mainly because I'm used to this. But you can think of real valued, and I think this all goes through. The point is that all abelian unitary sister algebras arise as continuous function on some compact space. Okay, so I'm using Gelfand duality here, and I'm saying that beta of X is the spectrum of the sister algebra of bounded functions on X, complex valued functions. And X star, it's really the spectrum of this quotient algebra, right? So you mod out bounded function by C0 functions, you get C of something, and that something is X star, is the remainder. All right, so how can I construct maps between such spaces? Well, let's start with something that we understand, so the naturals. First of all, I can use dualities, Stone duality, essentially, and notice that continuous maps from omega star to omega star, they do correspond to unital sister algebra homomorphisms from L infinity mod C0 to L infinity mod C0, but also to Boolean algebra homomorphisms of P omega mod phin. So if you look at the set of idempotents, so P is P star is P square in L infinity mod C0, that's exactly P omega mod phin. Okay, these are characteristic functions on subsets of omega mod phin, right? Because we mod it out by C0. Now, if I want to construct a map And an easy way to construct a map from omega star to omega star is to consider a finite to one map from omega to omega. And now, if I have properness, since I have properness, it's finite to one, when I take beta of f and I restrict it to omega star, I'm actually a subset of omega star. And I'm going to call these guys trivial. These are the ones, trivial maps are the ones which come from a map within the underlying spaces. And notice that if I start with an almost permutation, and here by an almost permutation, it just means that, okay, you can take out a finite set from the domain, a finite set from the codomain. Once you do that, you're really a bijection. Okay, so it's a bijection modulo finite. Yep.
Just to clarify, just not to confuse.
So if you're finite to one, the homomorphism, I'll call it trivial. Yeah, because it's an homomorphism. Beta f is trivial, yeah, I mean, whatever I induce on the Czech Stone. Because it's an homomorphism that I can understand. Okay? While if it's not, well, coming from something from the underlying, between the underlying spaces, I do not understand it. For homeomorphisms, trivial, well, okay, you say finite one, then you prove it's actually an almost permutation. It's an almost permutation, yeah. All right, so I can ask, okay, is everything trivial? And actually, the roots of this came from the question of whether this space here is homogeneous. I think this was asked by Erdős. Now, this space is not homogeneous, but the first proof I've seen is actually requiring CH. They show that under CH, this is not homogeneous. Doing that, they construct, well, we'll see, but they will construct non-trivial maps. And then they prove it's homogeneous without CH. It's Ulam, okay, so it's in the book. Okay, oh, so it's also Ulam. Okay. But they don't solve it, right? Yeah, CH is Rudin. Well, we'll see. But, and notice that there are only continuum many trivial maps. Okay, so right. So the question is like, is everything trivial? Let's focus a bit on homeomorphisms. So first thing I want to focus on is homeomorphism. And the first answer was provided by Rudin, Walter, who showed that under CH there are two to the continuum non-trivial. Well, there are two to the continuum autohomeomorphisms, and therefore there are two to the continuum non-trivial ones, right? Because there are only continuum many trivial guys. And in fact, with this, he actually showed that omega star is not homogeneous under CH. But it was still open at that point whether it would be consistent with set theory that all autohomomorphisms, all automorphisms of P omega mod phi, if you wish, were trivial. And Saron showed with oracle CC forcing, I think he introduced oracle CC forcing for this and other related things. He showed that in fact it is consistent. So there is a model of set theory such that in this model all autohomomorphisms of omega star are trivial. And later on with Yuri's stepruns, they showed that indeed this follows from PFA. PFA is the proper forcing axiom. It's coming. But, okay, but the consequences of PFA were actually used. And these are like not just consequences, but you see PFA as large cardinal strength. So to get PFA, you need some large cardinals, at least super compact. But these two axioms that are there, they don't. I mean, you can prove their consistency without any large cardinal assumption. So this is much weaker. So Boban Velišković showed that there is a C missing in Boban's name, but he showed that in fact it follows from OCA and MA, and recently with Ben, who is somewhere there, and Ilias, we actually showed that MA is irrelevant. We don't need MA for this. That's just CA. Okay. You could have proved it, and you would have saved us a lot of technical work. No, it's annoying. Oh, well, okay. Our proof is annoying, especially to write it. Okay, so just quick reminder: PFA is proper for an axiom. OCA is Stavo's open coloring axiom. This is some sort of Ramsey theory axiom. NMA is Martin's axiom, which is Baire category +1, I would say. And both of these guys, as I said, are consequences of PFA. They separately contradict continuum hypothesis. But when you want to force a model with these two, you don't need large cardinals. So this is weaker, all right? Okay, so what about maps which are not homeomorphisms? Because we seem to understand the situation with the homeomorphisms. Okay, maybe OCA is not optimal, but let's stick to the non-homeomorphisms case. Well, this was the weak extension principle formulated for omega, formulated by Ilias. In fact, he formulated it for more spaces, but this is what it boils down when one considers omega. So I think that following diagram is good. So what am I saying here? I'm saying this WEP holds for omega if you give me a continuous function from omega star to omega star, then I can split omega star into U0 and U1. So this is basically splitting the domain, okay? But once I dualize, I'm splitting the codomain sister algebra, okay? So U0 and U1, these two maps are just the inclusion map. Such that, okay, I have that U0 is small, the image of U0 is small, it's tiny, and on U1 I'm trivial, okay? So once you dualize that, it just means that your dual map, big phi, can be split, can be written as a direct sum of two things, such that this is trivial, and the map upstairs has large kernel. Large can be made precise here, I'm not gonna do it, but it's really meaning that the dual of phi 0, which is f restricted to U0, has nowhere dense range. Okay, so the image is very small, or the kernel of phi 0 is big, and phi 1, well, is trivial. So this is the weak extension principle in the case of omega, and now you can hope to prove that this is always true. But in fact, well, this is not always true because you have non-trivial homeomorphisms of omega star under CH, right? So you cannot have a Klopen set U0 such that the image is nowhere dense, because the image is always going to be Klopen if you're starting with an homeomorphism. And in fact, what Ilias showed is that this holds under CNMA, right? So if you assume, again, our lovely assumptions, you have this principle. I do suspect that somehow we prove that MA is not necessary. I would believe that, or at least I would know how to prove it. And again, this principle was formulated for reminders of all zero-dimensional spaces in some sense, and proved for like some of them, for ordinals and spaces arising from ordinals. But now, can we get rid of the nowhere dense part? That's the question. Like, is it consistent that in fact the nowhere dense part disappears? But the answer, so you would have some strong extension principle, but this is in fact not the case because of the following construction of Alan Dow. He constructed in ZFC, so you don't get rid of this, a non-trivial copy of omega star inside omega star. This one has nowhere dense range, so that's okay. It still fits our WEP context, but you don't get rid of it, all right? So you don't have a stronger extension principle, right? And as I said before, the WEP cannot hold under CH because of non-trivial homeomorphisms, okay? So this is what was known. And then with a student of mine, a master student of mine, we started analyzing what's the situation for other remainders. Well, first of all, we need to adjust a bit Ilias's definition. We need to fix it, I would say. Well, not fix it, just adjust it to the setting. So you consider, for example, like, let's consider the reals on one side and on the other side, just remove 0, 1, the open 0, 1. Now, these two spaces, the remainders are homomorphic, right? Because 0, 1 close is compact, essentially, so you cannot have non-principal ultrafilters concentrating on that. But good luck finding a continuous map from X to Y, which will induce a homomorphism, because the second X is connected and Y is not. So you would either concentrate on the left or on the right, and you will never get an homomorphism. So how do you fix that? Well, you basically, I will allow you to remove compact sets from either left or right. That's the plan. And this, well, gives the following definition. So this is the general WEP. I don't know who formulated this, because I've seen it in emails of me and Farah when I was still a student, and then we formalized it with my master's student some 10 years later. So you have a continuous map from Y star to X star. So X and Y are like, as usual, like they're small, they're non-compact, and they're locally compact. So you have a continuous map from Y star to X star. Then I can split Y star into two pieces, Gropen again. And then I will, as I said, I need to remove something. I need to take this Vy, which is an open subset. This is the open interval 0, 1. It's an open subset with compact closure. And then I have the same, right? I have that phi 0 as large kernel. So F restricted to U0 is small. And phi 1 is trivial. But in the domain of G, I remove this noise, this compact set that would basically forbid me from having continuous maps. So I have a proper continuous function G from Y minus the noise to X, such that beta of G restricts to F on U1. And I'm going to say that WEP holds if WEP holds for all pairs of spaces. And notice that I can get rid of the top part of the U0 in case F is surjective. Because if F is surjective, the dual is injective, so this one cannot have large kernel, okay? So this one basically doesn't exist. This is 0. That's the point. So I can conclude something trivial about all surjections. I can say all surjections are trivial. All right, and in fact, we show that it holds. I have to say that here, I think that by how the proof goes, because the proof of Ilias was using lifting theorems for Boolean algebras. Now we use lifting theorems for continuous functions on spaces which are like not zero-dimensional, so we don't have Klopen sets here and there, and we have to analyze how certain things sit in the Kalkin algebra. So I think one could remove MA if really one wants. But the problem is, like, you don't want to remove MA from this result. You want to remove MA from the results we use to prove this. And this is more annoying because there is some non-commutativity involved there. We use the Kalkin algebra a bit. But anyway, we actually proved something more because we are capable of doing what Ilias was capable of doing for powers. So we actually have a nice descriptions of maps between powers of Čech Stone remainders. In particular, you give me two integers, D and L, then every continuous map from the D power of a Čech Stone remainder to the L power of a Čech Stone remainder, it's trivial. It's trivial meaning that, okay, there is some noise, U0, and then there is a nice part that I can understand. So this just, it's not just for D equals 1 equals L, which would be WEP, or we can prove it in full generality for all powers. So before going to the coarse part, let me see how am I doing with time. That's okay. I want to just isolate some consequences of this principle. First of all, this I was able to prove earlier on. I can describe when two spaces have homeomorphic remainders, again, under our lovely assumptions. And basically, I can say that X star and Y star are homomorphic, even only if the spaces X and Y are homomorphic once I remove some noise. So let me see. This basically says that, okay, for omega, I have to take out finite subsets. Okay, here I have to take out this Vx and Vy. But basically, the only way to get that the remainders of these two spaces are the same, are homomorphic, is that, okay, I can take out some noise here, take out some noise there, and then on whatever remains, I do have a homeomorphism. Okay? So they must be homeomorphic modulo compact. And in fact, all homeomorphisms are trivial. Right? This was done before this WP. So I should come up with some questions. I don't know what's the situation under CH for non-zero dimensional spaces. So we all know that Pavlovichenko says that under CH, remainders of zero-dimensional spaces are all homomorphic, right? It's everything, it's beta omega minus omega. But in the one-dimensional setting, I don't know if everything has non-trivial homeomorphisms. I know it for many spaces. We know it for manifolds. We know it for, well, all zero-dimensional ones, obviously. But there are some tricky spaces I cannot understand. And the second question, yeah. Because otherwise, I believe you can create two very different spaces such that the remainder has 1 point, something like that. But yeah, let's like play with the long line. Yeah, and I mean the long line and omega 1, right? Have 1 point and 1 point. Yeah, it's small. More concretely, can you give me a space in a concrete way whose remainder is homeomorphic to R star under CH? And R star, it's really, you can think of the half-line star, right? Because R star is the disjoint union of the half-line, the left and the right. But can you find such an X? I know it exists using model theoretic considerations, let's say, but I don't know what it is. And I tried to shoot spaces and failed. For R to R square, actually, I don't know if there is one, because the model theoretic considerations that I use to show that there is one for R star, they don't hold here because continuous functions on this is not saturated on the remainder. It's not saturated in a model theoretic setting. We proved that. Right? So if you can find such a space, I would be happy. That's something I don't know. Let's go on with more consequences. Well, okay, we can characterize surjections. As I said, in case of surjections, so the map between the topological spaces is a surjection. So the kernel of this phi 0 has to be, well, phi 0 has to be 0, essentially. And that means that I don't have to take care of the nowhere dense part anymore. And I can completely characterize. And notice again that this phase under CH, because the half-line continuously surjects onto every connected compact space of the appropriate weight under CH. Right? But 0, 1 does not surject onto many spaces. And lastly, we can actually talk about powers. So we can use our result about powers, and we can prove that consistently, if you give me two nice spaces, and kappa is less than lambda, then you cannot surject x star square to y star. Let's say, but it works for all pairs of cardinals, finite, infinite. This was known for omega. I think used, I think it's used. Proved that consistently omega star square does not surject onto omega star, and then for every n plus 1 and n. And then in a zero-dimensional setting, this was known to work, but this worked for every space, for every x and y. And every kappa and lambda. All right, so let's move to the coarse setting. So first I would need to give an introduction of, well, a very, very quick introduction of what coarse geometry is. This is the study of metric spaces from very, very far away. So I'm saying that a function between two metric spaces is coarse if it maps coarse points, close points to close points. So you can unravel the formula, but what I'm basically saying is that if I have two parallel lines in the domain, they cannot go to two non-parallel lines, okay? So for every R, there is an S such that two lines are just sequences of points, in fact. They go to close things. You cannot have this. This is bad. All right? So this is coarseness. And then I'm going to say that two maps, sorry, if I have one map one way and the second map the other way, I'm going to say, okay, let's suppose that, so I go from X to Y, then I come back. And let's say that the error is bounded. It's a finite error, right? So think of like X is the reals, Y is the integers, and you take some, okay, this is the inclusion, one is the inclusion, and the other one is the smallest integer less than the point, right? So if I take the smallest integer and then I take the inclusion, the distance is 1, right? These two numbers are 1, something like that. And these things I'm going to call coarse equivalencies. So if F is coarse and G is coarse, and then I go, I come back, when I walk back, I don't see the difference. That's the point, right? So these are called coarse equivalencies, and the spaces are called coarsely equivalent, obviously. And this is the right notion of isomorphism here, right? This is my notion of homeomorphism. And these guys don't have to be injective nor surjective. In fact, as we showed, like even cardinality is not preserved. They just show that the shapes of the two spaces are the same. But the local structure, well, coarse geometry does not care about topology. Okay? I don't care about the local behavior. And it really behaves more like Morita equivalence or isomorphism up to multiplicity. You see, if you give me any space, I can double every point. The two are coarsely equivalent. I just send the 2 points to the previous one and the inclusion. All right, so this is more like up to multiplicity. And in fact, looking at coarse geometry or at spaces through coarse geometric lenses, it really underlies Gromov's approach to geometric group theory. And it has many applications in mathematics. I want to mention mathematical physics because we are here. But also group theory, transportation theory, semi-group theory. I've seen a lot of applications. And for the moment, I want to basically care about ULF or uniformly locally finite spaces. You can think of a Cayley graph of a finitely generated group. Okay? So this is saying that the balls are not only finite, but uniformly finite. So the balls of radius 15, they are less or equal than the number of generators of your group. 2 to the number of generators of your group. No, 50, or whatever. It's a finite number, right? I cannot compute. So again, balls are not only finite, but the size of balls of a certain fixed radius is uniformly bounded. And again, take Cayley graphs or discretized manifolds. That's something you can do, right, to get these spaces. And there is an abundance of sister algebras associated to such spaces, and they're designed to remember the core structure. And these fall under the name of Rowe-like algebra from John Rowe. And there is a program of understanding how much geometry is remembered by these sister algebras. Usually it is done in ZFC. And let's say that there has been a lot of work on this side. A bit far from set theory, I would say, but still Baire category it's used. So you can say set theory. All right. But when these algebras arise from quotients, well, ZFC is not enough. And the goal is to give you some examples. So I'm going to say that a bounded function is slowly oscillating if, well, the oscillation becomes smaller and smaller as I go to infinity. So what am I asking here? I'm saying, you give me epsilon and r, and then my function is good, is slowly oscillating, if, okay, so this is my space X. Well, now you fix epsilon, you fix r, Then I can find a finite f. So I don't know what's happening here. I don't care. It's finite. But now, here, if you give me 2 points whose distance is less than r, the function changes very little. Changes only up to epsilon. So f of x, so this is x, this is y, minus f of y must be less than epsilon. So you can change, but you do it slowly. Okay. So slowly oscillating functions do form a sister algebra. This is not difficult to check. You can sum these things, you can product these things, you can take adjoints, and it's norm closed. That's also easy to verify. And the spectrum, so now you have a unital sister algebra of L infinity of x. The spectrum is the Higson compactification. And then I can quotient, because C0 sits in there, because I can take out finite sets, right? So now the Higson corona is the spectrum of the algebra CH of x mod C0, right? So once again, here is the definition. And now I have this proposition of rho that said that if you have a coarse map between the underlying spaces, by proper, I really mean finite to 1, because everything is uniformly locally finite. Otherwise, you ask that the pre-image of every bounded set is bounded, right? So a proper coarse map from y to x is just to preserve C0, basically, the properness. It's going to give me a continuous map between the two Higson coronas. All right, so maps between the underlying spaces, they do, appropriate maps, like coarse, they do give you maps between our new coronas, our new remainders. And furthermore, if the original map I started with was a coarse equivalence, so this was my notion of isomorphism, well, then I do get a homomorphism of the spaces, okay? So this is perfectly fine. We can move from spaces to remainder spaces. And of course, the question is, can I go back, right? Can I characterize all maps between the coronas as maps arising from the spaces? Or I can even just ask, let's say that I have two spaces whose coronas are homeomorphic. Can I say that the spaces are the same, right? This iso should be homeo, right? So let's consider these two spaces, for example. So I take the squares, so 0, 1, 4, 9, 16. I don't know what's next, but you can figure it out. And then I take the set of pairs. So this is in y sits in R square. So this is the pair 1, 1, 4, 4, 4, 16, 9, 25, 25, 9, etc., etc. Now, these two guys are not coarse equivalent. This is not difficult to check. But when I look at the coronas, nu x and nu y, well, these are zero-dimensional. They're associated Boolean algebras, F-size continuum. They're atomless, and they're countably saturated. So Parovichenko says they're homomorphic under CH. So under CH, I cannot, if I have two homeomorphic coronas, I cannot get the spaces back. That's basically what I'm saying. And in fact, it was observed by Tarash, Banach, and Protasov that this works for all spaces which are zero-dimensional in the appropriate notion of dimension. Okay? I would say that they do it, they don't do it model theoretically. They don't prove these things above, right? You can prove, in fact, that the spectra are zero-dimensional, the Boolean algebras are countably saturated and atomless, but they do it in a constructive way, which is tough to follow sometimes. But it works, okay? And again, this asymptotic dimension, it's really the right notion of dimension here. This is what one should look at. But when I can raise the asymptotic dimension, it's not true that Higson coronas of spaces of a given dimension, so you fix dimension 5, it's not true that even under CH, they are all homomorphic. But it was proved by Will Bryan and Ilias for n equals 1, and then I extended it to n equals n. That under CH there are C pairwise non-similar spaces essentially that they give you the same coronas. Okay, so you can push Banach Protasov as much as you want. So you can find a lot of spaces which don't look the same, but the coronas are homomorphic. So now we need to go the other way, right? Because I don't know how to do it. I think I actually, yeah, no, you're correct. Okay, so let me see. Because they wrote it down. And I think they get 2 to the, I'll have to think. But I didn't write it down. So I want to be safe.
The C looks strange.
No, but you're correct. It should be. I can give you C many in a snap. I'll have to think. I can try to think later. Oh, now I'm thinking. Let me go on. Right. You're right. I want to get triviality. Okay. And again, remember that if I have coarse geometric.
Sorry.
Yes. Yeah, sure. The ULF. It's good. That's good that I didn't manage to find 2 to the C many. No, because the construction I have in mind, it's subsequences of a given sequence. So it's only C many. No, these are ULF. They're countable. Oof. Good. Okay, now I want to get triviality. So, as I said, if you have maps preserving coarse geometry, you do get maps between the Higson coronas, which preserve the topology. And now I'm going to say that something is trivial if it's coming from something downstairs, right? Okay, so now I'm going to formulate my coarse weak extension principle, which asserts the existence of a Clopen partition of the domain of the map, such that I'm trivial on U1 and I'm small on U0. This is the same thing. And surprise, surprise, it works. But it works only for injective maps between the coronas. I'm not saying it doesn't work for surjective maps. But it's enough to deal with homeomorphisms, obviously. So if I have homeomorphic coronas, I get the same space, so coarsely equivalent spaces. And in fact, all homeomorphisms are trivial. I can formulate these for injections. For not injective maps, I do get nice lifts. The problem is to pull out coarse geometric information. So I do squeeze my non-injective maps with whatever OCA and MA I need, and this squeeze, it's okay, I get the best I can get. The problem is to get out coarse geometric information unless I have injectivity. And this is something, I have to say I tried very hard, and I don't know how to do it. Okay, and you can make rigidity statements about embeddings. So, a couple of questions, and then we'll see if I have time to, probably not. A couple of questions is, does this hold for surjective maps? Obviously. And then, can I deal with power? I don't know this. I'm optimistic. I think this can be done. It should not be so painful, but I haven't figured it out yet. Also, this is very recent, so this was done in the last couple of months. Well, it appeared in the last couple of months. So, right, I think I have 6 minutes, so I'm not gonna tell you how to prove these things because this should be too much. There are 12 slides, so that's not good. But I want to highlight what we use, right? And I need to name drop a bit. And the 2 name drops, okay, first of all, I'm saying what OCA is, what Martin Axiom is. A big open question that you should all have in your head is whether OCA implies that the continuum is Aleph2. This is open. There are some partial results in this direction. Now, The idea is to use Stone duality, well, Gelfand duality, and to look at, this focuses on the topological setting. So I look at CB of X and C0 of Y, and the plan, the master plan here is you do have a map here, you want to lift, so you want to find a lift from CB of X to CB of Y, which it's well behaved. Okay, maybe you don't get it multiplicative, maybe you don't get it additive, but you can still, it's Borel in the appropriate setting. And from this Borelness, you want to squeeze out topological information. Okay? This is similar if you have seen Veličković proofs. Veličković proves that all automorphisms of P omega mod phi are trivial, and the proof can be split in two pieces. First, he proves that all automorphisms under OCA and MA have a Borel lift. And then it's a ZFC fact that if you have a Borel lift, you are trivial. Okay? And this is similar.
There is a step.
Yes. I mean,
Do you have it here?
not written down. Yes, but yeah. I think improve analytic is the same as continuous, but I think this is correct. The moment you take out reasonable compact noise, you want to take out, because in omega, compact noise is finite, so you can fix it. Here, you cannot fix it, right? So you want to take out some piece, and then yes, then it works. Yeah, like property of Baire implies continuity at infinity or something like that. I think this is true. Right. Okay. So pictures I drew, and I was very happy about them. The point is that we use these two theorems. This theorem of Paul McKenney and mine, which basically deals with maps from L infinity mod C0, so from reduced products inside C of Y star for some Y. So we can understand this. That's the point. We can lift these. Okay? And this is where I really don't know how to get rid of a MA. Or at least I suspect it will be painful. And after this, we also use, probably other results, but other previous results of mine. I just want to say one thing about the coarse version of this, which is fairly more complicated, because the nice factorization that I have of the C of X star into sub-reduced products of C-star algebras, here it doesn't work. So I don't know how to do it. I actually factor it into a finite sum of reduced products of Banach spaces. And then I don't apply these results that was here on the board by me and Paul McKenney. I do apply some other lifting results that we obtained with Ben last year. And then, and also, as I said, obtaining information about the spaces from well-behaved lifting, it's actually very painful, and I can only do it in case I deal with injective continuous maps to begin with. I don't know about the surjective case, but in the case of homeomorphism, I can do it, right? And I think that's it.